All right, it's 2:30, so let's begin. I hope you all had a wonderful holiday break. It's now time to ruin everything with circuits. So what we're going to be talking about today are Thevenin and Norton equivalent circuits. So we're going to be introducing two new circuit theorems today. So let's begin with Thevenin's theorem. So Thevenin's theorem states that any linear electrical two-terminal network can be replaced at the terminals by an equivalent voltage source VTH in series with an equivalent resistance RTH. So before we unpack what those equivalent voltage source VTH is and equivalent resistance RTH is, what is Thevenin's theorem telling us? We can take any linear two-terminal network and replace it with a practical voltage source, because a practical voltage source is a voltage source in series with a resistance, okay? So this is really just kind of a continuation of what we talked about prior to the break with regards to source transformations, but it's actually a little bit more powerful because we get to apply any linear circuit analysis techniques we want to determine those two quantities, VTH and RTH, okay? So let's define what our voltage is. The equivalent voltage VTH is the, change colors here for emphasis, open circuit voltage measured at the terminals of the live electrical network, where live in this case simply means that all of our independent sources, doesn't matter whether they're voltage sources or current sources, but all of our independent sources are on, okay? Our equivalent resistance, RTH, is the resistance seen between terminals of the dead electrical network. where in this case, a dead electrical network simply means all of our independent sources are turned off. Okay. So when we're determining a Thevenin equivalent circuit, we measure the voltage with all of our independent sources on over a particular set of terminals. And we measure the resistance with all of our independent sources turned off over that same set of terminals, okay? So let's look at a circuit. What we are going to do is we are going to find the Thevenin equivalent circuit as seen by one of these resistors, okay? So I want you guys to pick which resistor that we're going to find the Thevenin equivalent with respect to. The 6 ohm resistor, okay? So whenever we're finding the Thevenin equivalent voltage or the Thevenin equivalent resistance with respect to a particular circuit element, in this case, the 6 ohm resistor, what we do is we take the resistor out and we use its open circuited terminals where that component used to be to calculate our open circuit voltage and our effectively open circuit resistance as well, okay? So to find the Thevenin equivalent voltage with respect to the 6 ohm resistor, I'm going to redraw my circuit and I'm going to take that 6 ohm resistor out. So I'm replacing my 6 ohm resistor with an open circuit set of terminals. And my Thevenin voltage will simply be the voltage drop over this open circuit set of terminals. We can use any analysis method we want to calculate this quantity, VTH. So somebody tell me how to analyze this circuit for that quantity, VTH. What analysis method do you guys want to use? Mesh, okay? So using mesh analysis, I'm going to call this mesh current IA. This mesh current IB. Am I forgetting to include a mesh? Let's start there. I would argue no. Some of you who may not want to speak up, and that's perfectly okay, may believe that there is a third mesh current in the bottom right-hand corner, but I would argue that there isn't, because there's an open circuit there, which means that no current could flow around that third mesh, which is why I choose not to write one, okay? So we're actually only gonna have these two meshes to deal with. There are no current sources, so we won't have to do any super mesh technique or anything like that. This is just gonna be straight KVL equations. So Anita, I haven't seen you in a while, so I'm gonna pick on you. What should my KVL equation at mesh A look like? Let's start at the bottom left-hand corner and let's just follow IA around its path, right? So the first thing that we see is the negative polarity terminal of the 4-volt source. So we should start with negative 4 volts. Then we would see the 9 ohm resistor, which is I think where you were starting. You can start wherever you like. I just like to start at the bottom left-hand corner so that I'm consistent. What is the total current seen by the 9 ohm resistor, Anita? So IA is flowing down and IB is flowing up, right? So it's going to be some combination of those two. Since we're doing KVL around mesh A, the IA term should have the positive sign. And since IB is in the opposite direction, it gets a negative sign. Then we see the positive polarity terminal of our 3-volt source. And we are back to the node where we started from. So we set everything equal to 0. So that's our KVL at mesh A equation. Everybody okay with that? Perfectly fine. If you don't remember anything, we've all had 2 weeks of not doing circuits. So it'll take a minute to kind of kick everything back in. We can now do KVL around mesh B. Abby, do you want to help me out on this one? All righty. Sorry, I should write that better. That's supposed to be an 8, but I get you. If my stylus will write, there we go. And that's just going to see a mesh current of IB, right? Because we know that there's no current flowing in the other direction. All right, set that equal to 0. And we can take a moment and solve this system to determine our mesh currents IA and IB. All right, so these are the values that I got, but I'm using a Casio calculator that I'm relatively unfamiliar with because my TI's batteries apparently have finally died after some number of years. So there's a just non-zero possibility that I type crap in wrong because I'm not used to this calculator. So please let me know if I mess things up here or if you got these values. All right. So, Connor, since I believe it was you who suggested that we do mesh analysis, I would like for you to explain to me how we can use the results of that mesh analysis to determine that voltage VTH. I got both of them as positive. That equal sign there might have looked. Okay. So that likely, I believe the division there likely comes from the fact that the coefficient of the positive, or excuse me, the coefficient of the constant term for your first equation, when you move the -4 volts over, that's going to look like +4 minus 3 is +1. But I bet that if you put it as -1, you would get negative values for both things. That's really the only place I could see where that might come in, but yeah. All right, so I'm going to say that positive values are correct based on the polarity of the voltages. That would make the most sense to me. So let's circle back around to my question. How can we use the results of that mesh analysis to determine that quantity VTH? I'm asking Connor, but if anybody cares to help him out, by all means, do so. Anybody have any thoughts at all? All right, well, David. Current B minus current A times 6 ohms. Okay, I'm not entirely sure where any of that comes from. So, Norman. That's more in line with where my head is at. Okay, so let me write some things down here. I'm going to call this voltage V8, and I'm going to call this voltage V4. And I can write a Kirchhoff's voltage law equation around that bottom right-hand path that will effectively give me VTH, my Thevenin voltage that I'm looking for, is the voltage drop over the 8 ohm resistor with the polarity I've drawn, plus 3 volts, plus V4. The voltage rise of VTH is equal to the voltage drops around that closed path. Perfect application of Kirchhoff's voltage law. Everybody okay with the logic behind me doing that? I don't have any opposition. So let's talk about how we can figure out what V8 and V4 are. Okay. McKinley, any thoughts on V8? Exactly right. So that current IB is flowing into the positive polarity terminal. So that's just going to be 8 ohms times IB. And then we have plus 3 volts. Henry, what's going on with V4? This is a little bit of a trick question. going to be nothing. It is going to be nothing, but I think there's a more straightforward reason. Exactly right. There's no current flowing through the 4 ohm resistor because it's not part of a closed current carrying path. Therefore, the voltage drop over it has to be 0. So our Thevenin voltage is just going to be 8 ohms times IB. Plus an additional 3 volts, which I get to be 3.348 volts. So that's our Thevenin voltage. Everybody okay with that? All right. So now, excuse me, let's determine our Thevenin equivalent resistance. So I'm going to do the exact same thing. I'm going to redraw my circuit. I'm going to take my 6 ohm resistor out. All right, that should be 9 ohms. And ohms. And 8 ohms. All right, so whenever I am determining the Thevenin equivalent resistance with respect to a particular element, I take the element out and I look in through the open circuit terminals where the element used to be, but I need to be looking at a dead electrical network, which means I have to turn off my independent sources. So in this circuit, I have 2 independent voltage sources. So how do I turn off an independent voltage source? Replace it with a wire or a short circuit. Absolutely right. So this 4-volt source gets shorted out. This 3-volt source gets shorted out. And that's what I'm looking at. Okay. So while this isn't a wildly complicated resistor network, it has been a couple of minutes since we've done resistor combinations. So I'm going to go ahead and go through the steps of identifying my nodes and color coding everything so that I can easily see what's going on here. So right off the bat here, I call this node C. I can see that my 9 ohm resistor is shorted out. Let's call this guy A, this guy B, this guy up here D. Let's do the other ones. Let's do D in pink, A in blue, B in green. And since I'm trying to find the equivalent resistance seen between A and B, I'll put A on the left-hand side, B on the right-hand side. And to go from A to B, I can go from A to C to B. So let's put C here in the middle. So from A to C is the 8 ohm resistor. An alternative way from going from A to C is to go from A to D to C. So from A to D is the 5 ohm, from D to C is the 10 ohm. And then finally, there's only one path for me to go from C to B, which is through the 4 ohm resistor. So my equivalent resistance should be 15 ohms in parallel with 8 ohms. That combination in series with 4 ohms. Which looks like 9.217. Is everybody okay with the analysis we did there to determine, excuse me, I've got something in my throat, to determine our Thevenin equivalent resistance? We took the resistor out, made sure that we were looking at a dead network, and then used simple resistor combination techniques to figure out what the equivalent resistance we saw was. All right. So, may I go to the next page? All right. 3.34. So from the perspective of our 6 ohm resistor, it saw a 9.217 ohm resistor in series with a 3.348 volt source. So everything to the left here is the Thevenin equivalent, as seen by that 6 ohm resistor, okay? So it's just a different way of figuring out what practical voltage source is connected to an element of interest than using, back and forth source transformation techniques, which may or may not have even been available for us to use. I don't think there were any source transformations that we could have done with this particular circuit, but we wound up getting a practical voltage source. If, or a better thing would be when, you are asked to determine the Thevenin equivalent circuit with respect to a set of terminals, which is how I ask the questions usually on an exam, and what you'll see on your homeworks, or some of your homework problems. The steps are exactly the same. You just don't have to take the element of interest out because you already have an open circuit set of terminals to work with. Okay, and we'll work an example problem at the end of class to illustrate that. So before we move along to Norton equivalent circuits, does anybody have any questions about what we did here? Yes, Carter. Fantastic question, which I will answer on Friday. Today, we're going to leave things with only independent sources. And then we'll add dependent sources on Friday. So they're very good questions, which I have every intention of answering 48 hours from now. Yes. So the Thevenin equivalent will always be comprised of a voltage source in series with a resistance for these DC circuits. What we're about to talk about, which is a Norton equivalent circuit, is a practical current source representation. So it's where we're going to have a short circuit current in parallel with an equivalent resistance. Okay, so we'll get there in just a minute, as long as nobody else has any other questions regarding Thevenin voltage and Thevenin resistance. All right, so let's talk about Norton's theorem. Norton's theorem is very, very similar to Thevenin's theorem. It's interesting to me that the discovery, if you will, of these two theorems occurred, I want to say, almost 60 years apart, despite the fact of how crazy similar they are. So Norton's theorem states that any linear electrical terminal network can be replaced with, replaced at the terminals, excuse me, by an electrically equivalent current source, I Norton, in parallel with an equivalent resistance R Norton. The equivalent current I Norton, let me redraw that pen, is the short circuit current measured through the short-circuited terminals of the live electrical network. And finally, the equivalent resistance R Norton is the resistance seen in the terminals of the dead electrical network. So before we work an example that illustrates how to determine, excuse me, the Norton equivalent circuit, what is the difference between the Norton equivalent resistance and the Thevenin equivalent resistance? They're identical. There is no difference between Thevenin resistance and Norton resistance. They are both determined in the exact same way. You look in through the terminals of a dead network and see what resistance you see. Okay. So I am going to probably no longer use the term R Norton ever again. I'm going to leave everything in terms of R Thevenin because they're identical. So I want to revisit our circuit that we just analyzed, but now walk you through how to determine the Norton current. So I'm going to cheat here real quick and copy this guy. So that I have a picture of it that's a little closer. So this is our original circuit. We are going to try to find the Norton equivalent circuit with respect to that same 6 ohm resistor, which means for our short circuit current, we're going to redraw our circuit with the 6 ohm resistor taken out. So there's our circuit with our element of interest removed. But instead of figuring out what the open circuit voltage was or is, instead we're going to short these terminals. So we're just going to close them with a wire and find out how much current flows through that short, which is the short circuit current. Okay. So how would you care to determine that quantity, I Norton? Do mesh again, sure, why not? So let's call the left-hand mesh IA, the top right-hand mesh IB, and the bottom right-hand mesh IC. And now that we have a short circuit where our 6 ohm resistor was, it should be fairly obvious that our mesh current IC is going to be, or likely to be, non-zero, right? So our KVL at mesh A equation shouldn't change. -4 volts plus 9 ohms times IA minus IB plus 3 volts is equal to 0. Our KVL at E equation will change a little bit. Skylar, do you want to walk me through it? Thank you, ma'am. Equals 0. Thank you so much. That's absolutely correct. And obviously now we will have a KCL at mesh C equation. Mr. Darbone, help me out here. All right. Absolutely correct. So we now have a 3-equation, 3 unknown system. So let's take a couple of moments to put this guy in our calculator and solve. So these are the values that I got, again, using an unfamiliar calculator. So by all means, if I made a mistake, please correct me. Anyone able to confirm? Wonderful. All right. So, Abigail, how do these mesh currents help us solve for that current I Norton? It'd be something similar to that, sure, but I hope that effectively by inspection, we can just do it here, right? So how does that current I Norton relate to our mesh currents? So I Norton is the current that's flowing down through that short circuit on the bottom right-hand corner of our plot. Exactly right, just IC. You're overthinking it, I'm sure. Yeah, it is literally just IC. And we're not going to go through it again because it's pointless, right? But we would determine our Norton equivalent resistance the exact same way that we determined our Thevenin equivalent resistance about 10 minutes ago, and find obviously that we get the exact same answer of, I think, 9.217 ohms. So let me just double check. Yeah, 9.217 ohms. So from this, this is electrically equivalent to a 363.207 milliamp source milliamp in parallel with a 9.217 ohm resistor in parallel with our component of interest, the 6 ohm resistor, right? So the 6 ohm resistor sees either this Norton equivalent circuit containing a practical current source, or the Thevenin equivalent circuit containing the practical voltage source. It should not be remotely surprising that the Thevenin equivalent circuit and the Norton equivalent circuit are simply source transformations of each other. So we can say that, if my thing will scroll, V Thevenin is simply I Norton times R Thevenin, or I Norton is V Thevenin divided by R Thevenin, or R Thevenin is equal to V Thevenin divided by I Norton. This is just Ohm's law. 3 different configurations, right? So the concept of Thevenin and Norton equivalent circuits has a built-in method to check whether you did it right. Because if you know 2, you can calculate the third quantity just based on those 2, or you can actually go through the motions of doing the direct calculation. So calculating that short circuit current, calculating that open circuit voltage, or determining that equivalent resistance, right? So this is one of my favorite techniques because it's got a built-in way to check whether or not you did it correctly. So let's work one last example problem. And our ultimate goal here is to know V Thevenin, I Norton, and R Thevenin. And we are going to find these quantities with respect to that open circuit terminal pair on the right-hand side. Okay, so that means we don't need to take any elements out or anything. If we want V Thevenin, we simply take the voltage drop between those 2 open circuited terminals. If we want I Norton, we short out those terminals and to find out the current that flows through them. And for R Thevenin, we look in through those terminals. So, Colby, which one do you want to do first? V Thevenin, okay. So I'm going to be lazy again here. I'm just going to copy down this original circuit. Move it into place. So literally, the only change I need to make to this circuit to find the Thevenin voltage is to define the Thevenin voltage as the open circuit voltage. So what circuit analysis technique would you care to use? Let's do nodal. We've been doing mesh a bit. I'm going to choose this bottom node as my reference. So let's call this VA. Let's call this guy here VB. And let's call this guy here VC. Where a couple of things here. Obviously, we don't even really need to use a variable VA because we can see by inspection that VA is exactly equal to 3 volts. So that's going to be one of our equations. We'll use that in a minute. We don't actually have to use a variable VC either. Okay, now I'm going to, but I want to talk about why we don't need to. Henry, how much current flows through the 1 kilo ohm resistor? Just by inspection. You shouldn't need any math for this. The current flowing through the 1 kilo ohm resistor. Is the 1 kilo ohm resistor part of a closed current carrying network or current carrying path? No, because there's an open circuit connected on one line. So what's the current flowing through it? So what's the voltage drop over it? 0. So what that means is that VC and VB actually represent the same nodal voltage, because there's no voltage drop over the 1 kilo ohm resistor. So really, the only unknown quantity that we have is VB, which also happens to be our Thevenin equivalent voltage. Okay, so that's when you're comfortable doing those things, that's a couple of simplifications that you could easily make in your analysis, but let's go through the steps of doing this more formally, okay? Excuse me. So we have identified all of our nodes, labeled them, selected a ground. So obviously we have a voltage relationship equation. That is simply VA is equal to 3 volts. Since our supernode, remember, if we're applying nodal analysis, anytime we have a voltage source, we have a supernode. In this case, it's between node A and ground. And since our supernode contains ground, we do not need to do KCL at that supernode. We can move along to our KCL equations at our other nodes, right? So KCL at node B is going to be VB minus VA over 2 kilo ohms plus 7 milliamps plus VB over 5 kilo ohms plus VB minus VC over 1 kilo ohm is equal to 0. And KCL at C tells us that VC minus VB over 1 kilo ohm is equal to 0. We know that there's no other way for current to flow, right? So if we solve this system, obviously we'll find that VA is 3 volts. And we'll find that VB has some value, which I can't do in my head. And we should find that VC has the exact same value as VB. Let's throw this arguable system into our calculators. Let's see. Excuse me. So these are the results that I got. Please let me know if these seem correct. Norman gave me a thumbs up. I'm going to trust his judgment. So it should be fairly obvious that V Thevenin is just VC. This V Thevenin, the positive polarity, excuse me, the nodal voltage associated with the positive polarity of V Thevenin is VC, and the nodal voltage associated with the negative polarity of V Thevenin is ground. So V Thevenin is simply VC minus 0, or VC. So that gives us negative 7.857 volts for our Thevenin voltage. Anybody have any questions, comments, or concerns about this analysis? All right, forgive me if I'm misremembering your name, but Harold, is that correct? Which would you prefer to do next, the Norton current or the Thevenin resistance? Norton current, all right. Yeah, so we could, as a quick aside here, we could say that we know this bit right here is 0, which completely eliminates the need for this equation. And we could also say that this guy right here is 3 volts, meaning that we have one equation, one unknown. 100% we could do that. Yeah. All right. Mm-hmm. So in my calculator, I put it in as a 3x3 matrix. Yes. I didn't need to do that though. All right. So I'm pasting my circuit. What do I need to do to this circuit to determine the Norton current? Exactly right. I short circuit these terminals, and then I measure the current flowing through the short. 100% correct. Thank you. So I am going to make an executive decision here. Actually, maybe I won't. I was going to say that I'm going to do mesh analysis, but I changed my mind. Obviously, if we did mesh analysis here, we'd get a 3-equation, 3 unknown system where our third mesh, the one on the right-hand side, is exactly equal to I Norton. But I believe that using nodal analysis here is probably the smarter move. And the reason why I say that is because we only have one unknown quantity. We call this guy right here I'm just going to say Vx, right? That's the only unknown voltage in our entire circuit. Everybody understand why that's true? So we could write a KCL equation at node X, which would be Vx minus 3 volts over 2 kilo ohms plus 7 milliamps plus Vx over 5 kilo ohms plus Vx over 1 kilo ohm is equal to 0. I honestly don't have the foggiest clue how to use the numerical solver on this calculator, so I legitimately need you guys to tell me what the right answer is. So we could solve this one equation system for Vx. And then somebody tell me what Vx is supposed to be. Negative 3.235 volts. All right. Thank you. So how does I Norton relate to that voltage Vx? Vx divided by 1 kilo ohm. Absolutely correct. So that's just going to be negative 3.235 milliamps. I can divide by 1,000 all day. So we figured out what Thevenin is. We figured out what I Norton is. So I would argue that our Thevenin equivalent resistance will be nothing more than Thevenin divided by I Norton. That will be negative 7.857 volts divided by negative 3.235 milliamps, or 2.428, 2.429 actually, kilo ohms. And we can easily check this result by, everybody done writing stuff down. We can easily check that result by taking our original circuit, looking in when we turn off our independent sources. So Oren, how do I turn off my voltage source? How do I turn off my current source? Disagree. Open circuit. So voltage sources are turned off by replacing them with short circuits. Current sources are turned off by replacing them with open circuits. So we should be able to figure out what our equivalent resistance here is by pretty much inspection, right? We can see that the 2 kilo ohm resistor appears to be in parallel with a 5 kilo ohm resistor. That'll be in series with the 1 kilo ohm resistor. So 1K plus 2K in parallel with 5K. So that's 1 plus 10 over 7. 2.429 kilo ohms, which I believe is the exact same answer that we calculated, only knowing the Thevenin equivalent voltage and the Norton equivalent current. All right, unless anybody has any questions, I am done talking for the day.